Deep inside every single atom, there's this delicate balance. But what happens when that balance gets totally thrown off? Well, that's what we're diving into today, radioactivity. It's this incredible, spontaneous process that kicks in when an atom's core just can't hold it together anymore and decides it's time for a change.
Right, so what is it? What's the thing that actually pushes an atom to its breaking point? What's going on inside that forces it to just let go of all this energy and turn into something completely new? That's the big question we're tackling. And the answer, really, it all boils down to one word: instability. A serious imbalance right at the very heart of the atom. So when we say radioactivity, it's not some scary, complicated thing. It's nature's way of fixing that imbalance. Think of it like an atom's natural drive to find some peace and quiet, to get stable. And it does this all by itself, no outside help needed. Okay, so this instability usually comes from one of three main problems. First, you've just got way too many protons, all positively charged, right? And they're all crammed together, trying to push each other away. Or second, that delicate ratio of neutrons to protons is, well, it's all wrong. And finally, the third reason is the nucleus is just buzzing with way too much extra energy. It's in an excited state. All right, so how does an atom actually fix these problems? Let's look at the first strategy. This one's for a nucleus that's just too big, too heavy. To get stable again, it has to get rid of some serious weight, and it does that through something called alpha decay. The best way to think about this is to picture a skyscraper that's built way too high. It's overstuffed, it's wobbly, and before the whole thing comes crashing down, it just jettisons a whole chunk of itself to get stable again. That is pretty much exactly what a heavy nucleus is doing. So, what is this chunk that gets thrown out? Well, it's not random. It's a very specific package called an alpha particle. And an alpha particle is really just the core of a helium atom, two protons and two neutrons all bundled together. For the original nucleus, losing that is a pretty big deal. And here's how we write that out in the language of physics. You start with your original nucleus. Let's call it X. It's got a mass number A and an atomic number Z. Then, boom, it spits out that alpha particle, that helium nucleus. So what happens? Its mass number drops by 4 and its atomic number drops by 2. And what you're left with isn't X anymore. It's a totally new, lighter element we'll call Y. Now, this is the really cool part. The atom doesn't just go on a diet. It doesn't just get lighter. It fundamentally changes who it is. Remember, the number of protons is what defines an element. So if you lose 2 protons, you are no longer the same element. You've literally become your neighbor on the periodic table. Okay, but what if being overweight isn't the problem? What if it's more about the mix of particles inside? That's where our next solution comes in, beta decay. And this one involves a really wild kind of identity swap, happening right inside the atom's core. And it turns out there are 2 flavors of this. It all has to do with something called the weak nuclear force. See, if the nucleus has too many neutrons, one of those neutrons can just flip and become a proton. We call that beta minus decay. But if the problem is the opposite, too many protons, then a proton can turn into a neutron. And that's, you guessed it, beta plus decay. Either way, it's a super clever trick to get that internal ratio back in balance. Let's just look at beta minus for a second. Check this out. The mass number, A, stays exactly the same. Why? Because you just swapped one particle for another of roughly the same mass. But since a neutron became a proton, the atomic number Z actually goes up by 1. So the atom moves one step up the periodic table, and to balance the books, a little electron gets shot out. All right, on to our third and final type of decay. Now this one's a bit of a different beast. It's not about swapping particles or changing what the atom is. This one is purely 100% about getting rid of excess energy. And honestly, the best way to think about it is like letting off steam. After a big stressful event, like an alpha or beta decay, the new nucleus that's left over is often all worked up, it's jittery, it's in a high energy state. To chill out, it's got to release that pent-up energy. And the equation for this is super straightforward. See that little asterisk next to our starting nucleus X? That's just a little note to say, hey, this guy is in an excited, high-energy state. To relax, it just fires off a high-energy particle of light, a photon, we call it gamma ray, and settles back down. The key thing to notice is, it's still element X. It's the same atom, just calmer. So just to be super clear, with gamma emission, nothing about the atom's makeup changes. The number of protons is the same, the number of neutrons is the same. It's the same element. The only thing that's different is that it's gotten rid of its extra energy and is now in a much more stable, relaxed state. Okay, so we've talked a lot about how atoms decay, but what about when? Here's the crazy thing. You can never, ever predict when one specific atom is going to decay. But if you get a whole bunch of them together, they decay with the predictable, reliable precision of a Swiss watch. And this incredible predictability is all thanks to a concept called half-life. It's really simple. For any radioactive element, the half-life is just the amount of time it takes for exactly half of your atoms to decay. It is, without a doubt, the master clock of the nuclear universe. Let's make this real. Imagine you've got a substance with a half-life of, say, 5 hours, and you start with 8,000 of its atoms. Well, you wait 5 hours, and you'll have 4,000 left. Wait another 5 hours, and half of that is gone, so you're down to 2,000. It just keeps having and having with perfect timing. This predictable pattern is absolutely everything. And of course, there's a neat little formula for this. It connects the half-life to this other value we call the decay constant. And don't let the symbols fool you. This simple, elegant equation is the powerhouse behind amazing tools like carbon dating. It's how scientists can look at a fossil and tell you, with incredible accuracy, how old it is. Okay, let's do a quick recap of the whole story. Radioactivity, at its core, is just unstable atoms trying to find their happy place to get stable. If they're too heavy, they use alpha decay. If their internal proton-neutron mix is off, they use beta decay. And if they're just too worked up, they release gamma rays. And the whole process runs on the steady, predictable ticking of the half-life clock. And that brings us to one last big idea to chew on. We use this radioactive clock, this half-life, to peer deep into the past, right? We date everything from dinosaur bones to the age of our own planet. It is our absolute best tool for understanding where we came from. So here's the question I want to leave you with. If this perfectly predictable process gives us such a crystal clear window into the past, what could it possibly tell us about the future?